Quincy, you're the
So is it too bright? Is it like the lights here? Okay. All right. All right, so welcome back. Math 160. This will be my first time teaching this class, so sorry ahead of time. How do you guys feel about math? Like, I don't have any sense, like, to be honest. I mean, I could imagine in my wildest dreams that you all love mathematics deeply. Right? Is it true? No, okay. All right, so my wildest dreams. Not so true. Okay, shocking. All right, that's all right. So, well, I guess that what I want to do is I don't want to be overly ambitious with this course. I'd like to, you know, go over some concepts, right? Some mathematical concepts, how they're applied. We're not going to be super rigorous or, you know, be proving theorems or any of that stuff. So we're going to look and see how some sort of abstract mathematical concepts get, oh, not able to hear. Okay, hold on, thank you. Can you hear me now? Yes. I think a mic was off. I see no chat. Can everyone hear me? Nope. This is the worst. Sorry. Yes, you can hear me. Okay, good. All right, that's all I wanted. I'm happy. All right. So sorry for those that are online. I was just saying that we're gonna have a scaled down course. It's gonna be, I'm gonna try to talk about some basic math concepts. Let me actually just go to the Canvas site. So basically, I've broken it up into 3 modules. These are sort of the 3 topics we'll talk about in this course. The first is graph theory. As we go along, I'm going to add homework. I'm not going to like put it all on at once, and that's mostly because some things might take a little longer than I thought. I don't want to predetermine all that right now. But I'll have the homework for the next, whatever homework is due will be available to you after the last homework. Right now, there's a homework that's due on Monday. It's up here. So we'll talk about graphs. We'll start that today. There'll be an exam for graph theory. Same with statistics, and then social choice. There's going to be an exam, and it'll be the final exam. But it won't be cumulative or anything like that. It'll just be worth the same amount as the other exams. Other things to say about course. We have a text. Usually I try not, when I'm teaching the course I haven't taught before, I kind of lean on people that have done it. And so I'm using the text that was recommended to me. It seems fine. You know, if you weren't in love with the mathematics before, you may not be in love with the mathematics from this text. But okay. The subject is really interesting. You know, but we'll see. Hopefully it piques your interest a little. Not many prerequisites. Just having a little grasp of some algebra might be helpful. You know, again, I'm not going to be too picky here. Homework. So I didn't write. Usually I say I won't accept late homeworks, but okay, it's COVID. Everything's kind of screwy. I'll probably will accept it, you know, so long as there's a reason, right? But be in touch with me, okay? Let me know if there's something going on. Right? If it comes to the end of the semester and someone says I have, as has happened many times now, I tried to submit, you know, all the homeworks over the semester and none of them came in, and here they are. That's not very fair to me. To have to go back and regrade all of that stuff. So please just be aware of what's going on. If you're not getting grades, you should check your Canvas grades and make sure that you're actually getting graded. I will try to be timely with grading homeworks. So again, these, I think I want to say that these are set dates. Certainly for those that are in athletics or have other obligations, check these dates and see if there's a conflict. Let me know. We'll work something out. It's a small class. So participation is basically like, I want to say it's like an automatic 10 points for everybody, as long as you like show up. Just show up. That's all. Show up. Try to participate. Right? If you have a question, ask it. Right? We're all friends here, I think. And even if we're not, it's okay. Ask a question. So, but I will notice. I'm not going to take attendance. I'll notice if I haven't seen a student for like the whole time. Like it's not that hard. It's a small class, so that will affect the participants if you don't show up. Other questions about the syllabus, the structure of the course? All right. Dr. Kerr. I don't want to go around the room. I just feel like that's kind of like people want to, they can, but I'll do it after class. That's true. If the room's available. All right. Okay, so the first module and the first kind of part that we're going to look over, it's not done in sort of the order in the book. We're going to start with graph theory. Not really theory, just use of graphs. Okay. I will also, all of the lectures and the lecture notes will be posted on Canvas. So if you miss a lecture, if you're sick, you left it in or something, I'll catch that lecture, go to Canvas and check it out. Okay. I'll put them up there. If it goes like 2 days and it's a lecture hasn't been posted, just send me an email. There's a little post-production time. Usually I try to do it right after class, but sometimes I have a meeting and then it slips. So let me know. I'll get it up. I'm sorry, Ed. All right. So graph theory. So I want to talk about, this class is going to be, we're going to talk a lot about like applications. I'm not an applied mathematician. I love math for math. It's a great subject, but so this is very much not normal for me to talk about applications. But graph theory, they're everywhere. There are so many applications of graph theory that it's hard to like list. But you can think in social sciences. There's a ton of them. When you're trying to graph, like, for example, social networks or species or whatever. You want to form links, so on. For like, I guess they call them it's called operations research. But this is, I don't know, maybe people think this is like logistics. I don't know, like if you're running a business, this can help with, using graphs can help with this. Computer science is indispensable. If any of you are interested in programming or computer science, graph theory is all over the place there. But other sciences as well, like I have to say physical sciences, but biology, chemistry, graph theory. Even physics, like theoretical physics, I'd say some graph theory is present. And so what is it studying? It's studying connections between different entities. So I don't want to take everything at once, and this book is does I think a fairly nice job. Starts with these street routing problems. So we'll talk about these problems, and I'll try to bring in like some new, I won't just take stuff from the book. I'll try to bring in a few new diagrams and pictures and ideas. But we'll try to follow the book so you have some at home. So let me look at an example application. This is more in the operations research kind of world. Example is our section 5. There are a couple. So they start out in 5.1 with 3 street routing problems. So they call this, the first one is called the security guard problem. I'm a horrible speller, so sorry. Here's the problem. So, like a math in the webs. The Ypsilanti. I was accidental, but I did go to Ann Arbor for my undergrad, University of Michigan. Ypsilanti is the neighboring city. So nice to see this. Probably unnecessary comment. But there it is. And so what's the security problem? So here we've got some highlighted neighborhood of Normal Park. And you're a security guard, and the X here, this marks, your starting point. Okay. And your goal is to walk the streets. So what you want to do is you want to walk each block once. You want to just walk around. That's your goal. Like a simple. So I'm going to start at X. And then what do we want to do? We want to ask the following questions. So can we walk neighborhood, Normal Park? And with passing, so without rewalking any block, rewalking something, rewalking any block. Understand? People understand what I'm saying? So when I put X here, I'll just say that we're at that intersection. We start with that intersection. So I don't know the answer. I mean, it's a complicated neighborhood, Normal Park. But okay, that's one of the questions we're going to answer. So that's one question we can ask about the security guard problem. Another question we can ask is, if the answer is no, we'll find a way of telling right away. If not, what is the optimal route that covers the neighborhood? Maybe there are more than one. So optimal meaning, I can't get a shortcut. And I go through every block at least once. And then the third question is, can a better route? So let's say we answered one, it's no. Answer two, and then we want another question, can a better route be found? We start at a different point. Intersection say. So this is, I would say, almost too practical of a problem, right? I mean, it's like, this is, if you were a security guard, you probably would want an answer. Right? So it's too complicated. Let's see if we can. Well, I guess, let me ask you guys, since I don't want to talk too much. Is there like a very simple map you could draw where you could answer one in the affirmative? Like a very simple map.
Yes.
Yes. What would your map look like?
You can make it a square.
Yeah, great. Okay. That's a good map. Thank you. So here, so all of you guys can be security guards if your neighborhood looks like this. You will not need this course. Or at least this part of the course. Okay, that's true. I know, aim high, right? But okay, so however, if you just kind of extend it a little bit, I want to give away the punchline. We'll get to the punchline. Let's extend it a little. Okay, so how about now? Do it. I've left something out, right? I left out a starting. Say how we start. Can we do it? Yes. Yes. All right, so what if I'm feeling the security guard right now? What if the security guard has a coffee right here at X? So the security guard leaves his coffee or her coffee there, therefore must get back to the coffee. So at the end of the route, must be back at the coffee. Have you done? Yes.
Is that where they left the copy as well?
Yeah, they start, in other words, they start at X and they on the end of X. Yes, I see. Yeah, how many say yes? By a raise of hands, a forceful raise of hands. None of this stuff. I hate that. Good. Thank you. How many say no? How many forcefully say they have no idea? Fair, it's fair. I don't know is a fair response. I tell my kids that all the time. Yeah. All right, so the answer is no. Not if I want to get back. Yes, if I don't care, right? Why? Well, I start and I walk out. I walk around. I'm going to have to come back. I'm going to have to walk these two guys, right? These two blocks. That means I'm going to have to come back to X. If I come back to X, I'll have to leave X, right? Because I'll have missed this guy. So if I come back along here, I'll have to leave along there. But now I've used all three blocks connected to the starting point. So in order to get back to X, I'll have to retrace some steps. Similarly, if I left here and I came back this way, I'd have to go here. I would have used all three blocks. The point is X is connected to 1, 2, 3 streets. And 3 is not a number. And that actually prohibits me from being able to do this. We'll see that. We'll be able to answer these questions by essentially looking at some very simple features of the graph that we have in front of us, or the map we have. Determine the answers. Kind of cool little tricks. Very practical results. All right. Variants of this problem. They give 2 variants. Which are also fairly practical. One is the mail carrier problem. And it's the same. This is the same as the security guard problem, except for one thing. So mail carrier does need to get back to where they start. They start, let's say, at the post office. So they need to get back where they start. That. Back. Starting point. And then the second thing is that if we look at our map, some of these blocks we have, like, for example, this block, imagine there's houses on both sides. The mail carrier for those types of blocks will need to walk on one side and then also walk on the other side as well. So we'll have to take those blocks twice. We want to crisscross. Field. So now on the other hand, some blocks, like for example, this block, it only, that mail carrier is only doing houses on one side, so it'll only have to do that. So to say some blocks need to be visited exactly twice. Passing. So there's a variant to this problem. And then they have another problem they call, I don't know how standard this is, but they call it the UPS problem. Got my own UPS problem. So for UPS problem, so I took this map and then did a similar thing. So the UPS, they don't have to visit every house, right? They have a fancy truck or something, so they can get out. They don't have to go on both sides. They do run across streets all the time. Double park. And but they do have like an entry point and an exit point of the neighborhood. And they have like places they have to stop, and some places they don't have to stop. So for UPS variant, they only have certain blocks. Only certain blocks need to be visited once. And they have a specified entry and an exit point. Usually you'd say different. Not necessary. So these are three problems that I don't know if you would think of them as math problems. But they can be translated into mathematical problems. We could solve them using code. So while we're on the subject of streets, we might as well talk about Euler. I don't know, grandfather of graph theory. Will you allow me that? Even if you won't. But Euler, not Euler. Famous mathematician. You guys all know Euler, right? Who's ever heard of Euler? Solid raise of hands there. He is like an interesting guy. We're dead. For like a few hundred years now. You guys have all heard of exponential growth, right? Right? You guys have all heard of like natural log, right? Maybe. Nobody likes that. Don't ask. Has anyone taken calculus in this class? Why would I be here? Well, okay. Yeah, if you haven't taken calculus, at knowing what the natural log is like a ridiculous idea. So the fact that they teach that in high school is just awful. Awful people. Anyway, I guess I'm being important. Okay, well, you know this, right? E to the x. Have you ever seen that? E is the number E, right? That's from this guy. He's for Euler. The name is a number named after the first letter of his name. What a guy, right? Okay. He was really old when he died. unlike a lot of mathematicians, die young, just like rock stars. First name Leonard, I think, or anyway, blind, still did math, like dictated to his grandchildren, really good grandchildren, that take dictation from their blind grandfather and write down math formulas. It's awesome. I'll aspire to that. Anyway, enough about Euler. One of his, he's like known as a guy that came up with some basic applications of graph theory. And here's one that goes way back. It's a classic. So, Bridges of Königsberg. Side. Super prolific, wrote a ton of math. I don't know where Königsberg is. Definitely somewhere in some German. I'm going to draw the sketch here. These are rivers. This is a river. So there's 3 rivers they meet. Near Königsberg. There's an island. So here's my rivers. These guys love bridges in this town. They built a bunch of them. Built a bunch of bridges to the island. Okay, it's a bigger island. A lot of bridges. All right. So red is the bridges. And it's in black. White is in blue. Okay. So the question. First question is, you're a tourist in Königsberg and you love bridges and you want to visit each bridge, but only once because you really don't love them that much. Can you visit? Visit, I mean, pass. Have you done? Okay, where do you start? Helicopter there. I keep on looking for my coffee. Make a bad decision. All right. Do people have a thought? How many people think they can? How many people think they can? Can'ts are right. Can'ts aren't always right. Don't always raise your hand. I know there's no answer. But again, this last couple cases, the can'ts are right. And we'll see why. A little bit later. I want to develop a little more. There's also the bridges of Madison County. I don't know what to say on this. Okay, I'll draw it. Maybe we can reference it. Same question, and maybe we'll bridges. Madison County. New special on. a really small island. A lot of bridges are really small. Okay, so here's the water. This whole thing is the bridges. Bridge. We should. Okay. So similar kind of problem here. I think with the Madison County one, they label the islands and they say, can you start on one island and end on the other? If there is a solution. That's the more precise problem. So it's a slight variant. All right, so these are street routing problems. These are basic problems that if you're a tourist, or if you deliver mail, or if you're a security guard, would have real practical consequences, right? You would say, okay, I'd like to solve this problem. Now, certainly for like UPS or for companies, right, they write computer programs using graph theory to solve these problems. So they code a lot of this, and then a driver can go into their truck and put into the computer and say, okay, give me the route, and it makes an efficient route for it. This has very practical consequences for the business, right? Of saving a massive amount of time and fuel. So these are good applications, practical applications as well. Just one tourist application. But we haven't really done anything that we're applying. And so what does mathematics do for us? It strips away all of the human, from any situation, humanity from anything, and like just looks at it as a cold, hard, like reality, right? I don't know what to say, right? There's no story in math for the bridges of Madison County or Königsberg, or there's no mail carrier. There's none of those. We want to take all of those things away because they're sort of, that's too much poetry for one person. For me, we have to take it away, and we just have to give ourselves some abstract things that we can then take any story, like any of these situations, and use this theory, this model, to really answer questions. So we want, like, that's the mathematician's way, and we want to just do it for fun. So let's do it. So let's get this really just sort of dry but bare bones kind of structure that we can apply to all of these situations. So these are graphs. I know you're already mad at me. Sorry. Nothing I can do about that. But they're not the graphs you see in high school. Now maybe you're less mad. Right. You know, like this is a graph, y equals f of x, right? Not the graph I'm talking about, right? This is not the graph. Different graph, totally different notion. This is not what I'm talking about. We're not talking about that, at least not now. Probably not ever. But never seen it. We're talking about a different kind of graph, a mathematical graph. What is a mathematical graph? That's not to say that those other things shouldn't be called graphs, just a different kind. Totally different notion. Our mathematical graph has two things. It has vertices. Two things. We'll decorate and make these, give them all sorts of extra structure if we want. Say things. Vertices and edges. And what are our vertices? Well, our vertices are abstract vertices. Think of them as elements of an abstract set. Oftentimes we'll identify them with a label of some sort, like a letter, okay, or a name. So our vertices are going to be, we're going to identify with a vertex set. And for that, I want a little notation. It's going to equal, I'm going to put curly brackets for sets. Okay. Curly brackets for sets. And well, the book uses Roman letters, capital Roman letters. Of course, you know, you can use lowercase or you can use words, you can use pictures if you want, whatever. It's just a set of things that identify your vertices. All right. Set of labels. But you can actually identify them with your vertices. And then you have your edge set. An edge set, well, you want to think of this as just labels identifying edges, but you can sort of label the edges by the two vertices an edge connects. So you can say A, C, A, and we're going to allow ourselves to be able to sort of do something like this. Maybe put a little tilde or something on it. In other words, we'll allow multiple edges from two vertices. So let's say let me give you this. Let me draw this example. Hopefully this will make sense. This is an example. So I have three vertices, A, B, and C. I'm going to make them pretty big. Oftentimes you just make them little points, but I'll just put a little bubble around it. Now my edges connect vertices. So AC is one of my edges. I'll connect it. Connect A and C. BC connects B and C. AA connects A with itself. So I draw a little loop. I've got another, this tilde just denotes that I've got a different edge, but it's still connecting B and C. So I'll have a different edge, but another one. Okay. All right, guys. How's everyone doing? Make sense? Questions about it? All right. This is what a graph is. Spend the next, I don't know, 4 weeks talking about graphs. But this is what a graph is. It's a set of vertices, a set of edges. We may eventually direct our edges so they have they go in one direction versus another, right? We may eliminate loops or multiple edges, things like that. Maybe talk about other situations, but we're going to talk a lot about these types of structures. I'm going to see how they can be applied in many, many situations, including the ones we just talked about. In order to do this, we need a lot of vocabulary. So let's talk about some vocabulary. Okay, so I've got, you know, a list of notions here. Let's talk. You guys can tell me. Most of these are self-evident. Adjacent vertices. Okay, we call on the class. Who can tell me a pair of adjacent vertices in this graph? Can't hear you. A and C. Very good. Why do you say that? Next to each other? They connect. There's an edge connecting. That's great. So A and C are adjacent because there's an edge connecting. B and A, for example, however, these guys are not adjacent in our language. Even though they're close to each other, there's no edge. Okay. Adjacency, this means that an edge. Next. Okay, so multiple edges, I think can see what's going on. So multiple edges. Sometimes I don't know if I didn't read closely enough. The book might write something like this, where you see this twice. There is a notion of something called a multi-set, where you allow repetition and maybe draw two. I prefer actually sort of distinguishing them, though, to be honest. But all right. Multiple edges just means that given two vertices, there may be more than one edge connected. Edge. Connecting vertices to given vertices. Oops. So I know you may be like, come on, we can see all of this. This is like ridiculous. It's just English. You're using English. This is not math. It's true. But there's actually, you want to know the difference between certain things. Okay. So there's the language is fairly specific. And so we have to be a little bit careful. So a loop is it's an edge connecting a vertex to itself. Now, the point that I'm trying to make here about being careful is that I could give you another graph. Let's say I give you this graph, and here I'll just use vertices like points instead of circles here. So let's label them A, B, and C. I could give you a graph like this, right? Let's make a little triangle or something. You can say, I can make a loop, right? I start at A and I go here, here, and here, and I've made a loop. Okay, that makes sense in maybe English, but that's not what a mathematical loop is. That actually has another name. That's called a circuit. So we want to distinguish between these two things because they will have questions and we want to answer them correctly according to our language. All right, so now let's get one that we will use a bit and maybe you have not heard of, the degree of a vertex. So the degree of a vertex is the number of half edges connected to that vertex. By which I mean, if you just took a little bubble and put it around your vertex, you would look at these and you cut these edges in half, say, and you would count the number of half edges there, and you would get through. If you did that here, you would also get through. The point is you don't want to count this only once. All right. Click. You guys all know clicks. You went to high school, right? What I'm talking about. What's the graph? You guys are like, yep. So what's a graph theory version of a clique? So this has to do with sort of friendship net. So if you look in the book, they talk about like Facebook friends, making a graph from Facebook friends, which Facebook does. And okay, so what is a clique like? Everybody knows everybody, right? They're all friends with each other. They're a clique. Okay, so a clique is it's a subgraph of a given graph where everybody knows everybody. So let's say there are 4 friends there, and when I draw an edge, that means that they're friends with each other. 4 people. Edge means friends with each other. So this is a clique. All of them are friends. So this is a subgraph. Subgraph meaning a subset. Well, hopefully subgraph is kind of makes sense to you. Where, if not, then we'll talk about them. All right. So now what's the opposite of a clique would be like an isolated vertex. It's like, like a very lonely person. So it's just a vertex with no connect. No, this is like my Facebook. One is the loneliest number. I guess this is not. Friends myself. One time. Okay, so I've got 1 minute and I've got about 4 more. I'd rather actually save the next ones. Let me say one more and then I'll save it for next time. We'll talk a little more and then we'll apply these notions to the problems that we had. And
Thank you.
So I shot you an email like right before class.
yeah, if I saw you come in with your hat.
Yeah, I was like,
It's not a problem.
I got out there and I was parked, it was like 12:15, and then I was like walking in the building, I was like, oh, I need my mask.